So for this week, you have no assignment. Okay, meaning you don't need to hand in anything, but you should still doing that assignment. It takes 2 weeks. So the first part of the assignment, there are 2 questions in the problem set number 7. Okay. The first question, task 1, is to repeat this experiment, okay, so that you can understand some property of the central limit theorem. This task 2 is to calculate some confidence intervals, okay, which is relatively easier. So we will do the task 1 this week, and then we will do the task 2 next week. Okay. So it's very difficult to understand what is going on with these all histogram. Okay. So we need to repeat such experiment together so that you will have better understanding of some property of the central limit theorem. Okay, and so I want to introduce a function called range between, and it accepts 2 arguments. The first argument is the bottom. Okay. Okay, let's type in the numbers and then I will tell you what is going on. Okay, the bottom is 1 and then the top is 6, and it gives me 4. But your results may be different. Okay. So what the range between does is that it selects the random number from the bottom to the top. Okay, 1 to 6. Okay, randomly select a integer from 1 to 6. So for this time, it gives me 4. Okay, but you may have different answer because it's random, right? So by using the range between, we actually simulate a dice, okay, a 6-sided dice, 1 to 6. Okay, but there are different type of dice. For example, D20. There is a 20-sided dice, and if you play the games like Advanced Dungeons and Dragons, you will see the D20 dice, and there is even some D100 dice, which is like this. Okay, but that is not the point of the discussion today. Actually, we will just use the 6-sided dice, the ordinary dice. So we can roll the dice, roll a 6-sided dice 1 time, which gives me 4 for me, and you can populate it like 10, and then we are rolling the dice for 10 times, and you can see that the answer is a little bit different. It's not 4 anymore. Again, because this is randomly selected. So, yeah, again, if you are playing Mahjong and you have low dice at your hand, you can use Excel next time. Okay. And so now we have the random number generator, and the task 1 is to do the simulation of rolling 1 dice, 5 dice, and 20 6-sided dice for 5,000 times, and then plot the sample mean of the score from each trial as a histogram. Okay. So let's do the one dice situation. Okay, so D1, meaning we only have one dice. Okay, and we don't need to roll it for 5,000 times. So range between and then 1 to 6. Because we need to roll it for 5,000 times, you can just jet it to 5,000. Don't do it, okay? Because it takes too long. So we will use a faster method. Which is using the name box A2 up to A5001. And then Control D. And then we roll the dice file for 5,000 times. Okay, we have we did the experiment, rolling the dice for 5,000 times, one dice. And then each row represent one trial, meaning rolling it one time. Okay, and then we need to calculate the sample mean for each trial. Okay, for one die situation, it is stupid, but because we want to formalize the experiment, so we still need to do it. Okay, we calculate the average of A2, and then you will find that it is actually the same. Because when you're averaging one number, which is the same number, but for the sake of the experiment, we still need to do that. And then using the name box, select B2 to B5001, and then Control D. And then I have calculated the sample mean for all the trials. Any problem so far? Okay. The sample mean is just the average of A2. So the result should be the same because you only have one sample. When you're averaging one sample, then it's actually the same. And then we need to, as the answer request, we need to plot the histogram. Okay, a histogram actually is like this. Okay, do you remember the bell shape here, right? This is the normal distribution. And this is actually a histogram. And a histogram is the plotting the frequency for each range of the score in that frequency. And then we plot it, and then we will get a, for example, if the underlying distribution is normally distributed, and then you plot it, you should get a bell shape. Okay. And how to do it? So you need to first define the bins, and then the frequency. The bins is the range of the data for each bar. So, and actually you can use different bins, but for us, we want to use a 0.5 bins. And select that two cells and then populate it up to 7. Okay, and then what we need to calculate is the frequency for each bins. For example, that bins will be the number, the frequency of the trial that have the sample mean lower than 0. And that one will be 0.5 to 0, and then that one is 0.5 to 1, and then that one is 1 to 125, the frequency. Okay. And you can count it by hand. Okay, for example, 3, 3, 3, and then count how many of them are 3. Okay, again, don't do it. We can use Excel to do it. But I need to introduce a concept called the array function. Because we want to calculate the frequency for each bins. So the method is, first, select the frequency, all the frequency, empty frequency cells. Okay. And then equal. We will use a function called frequency. And it should accept 2 arguments. The first argument is data array. The second argument is the bins array. And the data array is our sample mean because we want to plot the histogram of the data of the sample mean. So it should be B2 up to B5001. And then the bins array is D2 up to D16, and then close it. But don't hit enter. You can try it, but don't do it. Okay? If you are using our Mac, okay, no one using our Mac here. Okay. And it is actually meaning that we will have a different key combination for each computer. For those who are using a Mac with Microsoft Office 2016, the key combination should be Command-Shift-Enter. For those who are using Windows PC, it should be Control-Shift-Enter. For those who are using a Mac with Microsoft Office 2011, which is this computer, or using the older version of Mac, the key combination is Control-Enter. Okay, I will tell you your key combination individually. Okay, for your computer should be Control-Shift-Enter. 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 Oh, no, Command-Shift-Enter. 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 And Command-Shift-Enter. Control-Shift-Enter. That one should be Command-Shift-Enter. Command-Shift-Enter as well. And Control-Shift-Enter. Okay. Really? After you do that, the result should be like this. Okay. because we need to change the behavior of the function so that it return a range, a number of cells, not single cell, multiple cells. So you should get the answer something like this, but the numbers may be a little bit different because that is random, right? So the meaning for this number is there are 821 shells, 821 trial with the sample means ranged from 0.5 to 1. Okay, it's actually meaning 1. Okay. 8 something, and then that one is 1.5 to 2, that number. Okay, and that one is 2.1 to 2.5, that is 0. So that is also what we expected. And then if we plot it as a histogram, so this time we need to plot the histogram. So, but there is no direct method to plot the histogram in Excel. So pay attention. Okay. Select all the frequency. And then charts, insert a column chart. You should get something like this. But the problem with this chart is that the x-axis is not correct. For example, it's saying 3, but actually it should be 1. So we need to change that. So the method is select, click the bars, and then right click, and then select data. There should be a category x-axis labels, and then select the bins. And then hit OK. You should get the chart like this, but it is still not the histogram we expected. So click the bars again, format data series, and then change the gap width to 0. If you did everything, the histogram should look like this. The x-axis is the sample means, and the y-axis is the frequency. Okay, for some users, particularly those Mac users using 2016, there may be some problem if you use the data selector. So the method is to copy the formula in the y-axis. Okay, it's actually meaning this. Paste it and then change it to B. Okay. That is the histogram we expected. So what you can see from that histogram. the probability of rolling 1 to 6 is roughly equal. It's 800 something. The difference is a little bit different, but it's roughly 800 something. So why 800? Because we did 5,000 trials, right? But we only have 6 outcomes. So 800, 500 divided by 6 is 800 something. Okay. And does it look like a bell shape? No,
No.
right? This is a distribution, we call it uniform distribution. It's not randomly, it is not normally distributed. Okay? Okay. So, write something here. When the n equal to 1, the histogram is like this. Okay. And it is not normally distributed. What's that? Okay, the second thing the question asking is to calculate the means of sample mean and also the standard deviation of the sample mean. So you know how to do it, but mean of sample means and also the SD of sample means. So which is actually equal to the average of B2 up to B5001 and also the standard deviation meaning STDEVPA of B2 up to B5001. So your answer should be in that range. 3.5 something, more or less 3.5, and the standard deviation of 1.7 something. So write it down. Roughly 3.5 and roughly 1.7. Actually, theoretically, we all know that the average should be 3.5. Actually, we haven't touched anything about the central limit theorem. So when we increase the sample size from 1 dice to 5 dice, and 5 dice or 1 dice to 20 dice, we will see what is going on with that central limit theorem. Okay. So we now increase the sample size from 1 dice to 5 dice. Okay. Okay. We call that one to be dice 1. The name of the workbook. So we can create a new one and then change it to dice 5. Okay, meaning that workbook is for a 5 dice experiment. So this time, instead of only D1, we have D1, D2, D3, D4, and D5. Because we are rolling 5 dice. So again, when between 1 to 6, and then we copy it to up to E. So each one of them have the range between 1 to 6. Can you use the populate? Actually, I don't think so. Okay, you can use the population to populate the formula from A2 to E2. And then we need to calculate the sample mean for each trial. So for the F column, F2 shell, it should be the average of A2 up to E2. So we roll 5 dice together and then calculate the mean of all those 5 dice. The outcome of those 5 dice. And for my experiment, my first trial, it gave me 4.4, but your answer may be a little bit different. Really? The last time I did that, it gave me 1 point something, which is meaning I'm truly unlucky. So again, we need to repeat that experiment. Repeat that rolling dice for 5,000 times. So again, you can populate it up to 5,000, but don't do it. So we have a quick way to do it using the name box. In the name box, type in A2 up to F001, and then Control D. A2 up to F5001, and then Control D. It will populate all the shells. And then you can see that it's roughly 3.5 something, but there is sometimes it get to 4.6 and 2, maybe some 1 point something. Okay. And again, we plot the histogram, bins 0, 0, and then 0.5, and then create all the bins to 7, and then calculates the frequency. Frequency of F2 up to F5001. And it's and then the bins array, H2 up to H16. It should give you something like this. And plot the histogram. you should have a graph like this. The shape may be a little bit different, but roughly like this. And then we can calculate the average, the means of sample mean, and also the SD of sample means, which is equal to the average of F2 up to F5001, and also the SD, the EVPA of F2 up to F5001. So when we repeat the experiment for 5 dice, compare and contrast the shape of the distribution. One die situation is not normally distributed. But for the 5 dice situation, it looked like a bell to me. So it looked like this. Roughly around randomly distributed. That is something from the graphs. And also the means of sample mean is still 3 point something, 3.5 something. And the SD of the sample mean become 0.75. This is the first property of the central limit theorem. The first property of the central limit theorem is that regardless of the underlying distribution of the data, if you take a random sample from that data, okay, and then calculate the sample mean, and you repeat it multiple times, it will become normally distributed. And that distribution have the same means to the population. And then I will talk about the standard deviation when we increase the sample size to try. So we still have time to do the 20 dice situation. So the final one, we further increase the sample size from 5 to 20. Okay, so we repeat the same thing. D6, D7, D8, D9, D10. Okay. And actually, you need to create 20 columns. And then for each one, use the range between to roll 1 dice, and then populate it up to D20 column. And then same token, calculate the sample mean for each child, which is the average of A2 up to T2. So you get 3.6 something. And then we repeat it 5,000 times. U5001. And then Control D. So we repeat the experiment by rolling 20 dice simultaneously and then calculate the sample mean. And then you get something like this. And histogram again. Do it really quick. again calculate the means of sample mean and the SD of the sample means, which is equal to okay. If you do it quickly, like I do, what you will find here is that okay, in the 5-die situation, the data spread from 1.5 up to 6, okay? And in the 20-die situation, you can see that the spread of the data is from 2.5 up to 4.5 something. And actually, there's very small cases with 5 and 2.5. Okay, the spread of the data reduce when the sample size increase. It also reflected in the standard deviation. For example, in the 5-die situation, the standard deviation is 0.7 something, and in the 20-die situation, it's 3.7. Okay, the standard deviation actually is measuring the spread of the data. So when it reduces, it's actually meaning less spread, or meaning more accurate, kind of. But the means of sample mean is still 3.5. So what we can see here is that, again, the sample, the histogram is still look fairly, so it's still normally distributed, but the spread of the data reduce, so it becomes sharper, the peak. And the means of sample mean is 3.5. The standard deviation reduce. So actually it reduces as a function of square root of n. So even though for this one the increase is like a 50 times, increased by 50, the standard deviation is just reduce it a little. But for that one, the reduction is like very large. Even though that too, the sample size increase is very big, the reduction in the standard deviation is not that big. So it reduces as a function of square root of n. So, yeah, that is the second property of the central limit theorem. Because we know that the distribution of the sample mean will approach normal. So we can use the normal distribution assumption to calculate the confidence intervals. Okay, we will calculate the confidence intervals next time. And for example, but in the real life, okay, you will only do one experiment, right? You will only do one survey. You will not do multiple survey. So what you can get is just one row of data, right? It's not multiple rows. And then what you can get is just a sample mean. But because you get that sample mean, but it's somehow still very close to the population mean. We know that the population mean is 3.5 something, but when you do the experiment, you get 3.8. So you can use that sample mean to predict the population mean. So that's why you can use one sample to infer the information about the population. And then when you increase the sample size, the accuracy as reflected by the standard deviation increase. So for example, in that case, for example, in the 20 die situation, the sample size is 20. You can see that most of the data is roughly 3.5 and something. There is no much extreme here. But in the 5 die situation, there is many extremes. For example, okay, if you are unfortunate enough and you conduct just one experiment and then you get 2, you may be in trouble because it's not 3.5. So increasing the sample size also increase the accuracy of your estimation. If you have time, you can try to do a D100, 100 sample. Try to increase the sample size a lot, and then you will see that your estimation will become very accurate. So yeah, again, you should know a little bit more or more clear about the concept of the central limit theorem by now. You should, but I don't know whether you can. Again, there is no assignment this week. I mean, you don't need to hand in an assignment by next week. You can still do the assignment by yourself. And that's all.